Welcome back to Physics 142 Online. To close off this section dealing with the sources of magnetic fields, we're going to introduce another fundamental law called Ampere's Law. And thinking back to our study of electrostatics and how to calculate electric fields, we learned that we can always use Coulomb's law in the expression for the electric field produced by a charge distribution to calculate that electric field. But that in certain highly symmetrical cases, Gauss's law gives us a shortcut, a much easier way of finding the electric field if the symmetry is present. Likewise, when we want to calculate magnetic fields, we can always use the Biot-Savart law to find the magnetic field of any current configuration, as long as we're willing to do calculus or turn that into a numerical calculation. But when the current loops or the current shapes have high symmetry, there's a shortcut. And that shortcut is called Ampere's Law. So what this means, and this harkens back to those standardized test questions that you've probably had before, Ampere's Law is to the Biot-Savart law as Gauss's law is to Coulomb's law. It gives us a way of finding the magnetic field in a very short number of steps, very small number of steps, if the symmetry of the current configuration is high. And here we'll just write down what Ampere's law is. Rather than try to prove it, I'm going to write it down for you and then demonstrate that it gives us the right answer in a special case that we already know the answer to from the Biot-Savart law. You'll notice that it has a very similar form to Gauss's law with one exception. On the left-hand side, there's an integral over a closed path or a closed loop. In Gauss's law, we had the integral of E dot dA over a closed surface. So the dimensionality is a little bit different. On the right-hand side, there's a fundamental constant, and then there's an enclosed current, where if you remember from Gauss's law, that was equal on the right-hand side to an enclosed charge divided by a fundamental constant. So there's similarities between the two expressions, but they express slightly different ways of doing the calculation. The integral, therefore, is over any closed loop, and I enclosed is the current that threads through the surface that closed loop defines. Clearly we need to do an example so that you can understand what's going on here, but the important part is, just as in Gauss's law, you had to choose a surface over which to evaluate Gauss's law and then ultimately solve for the electric field. Here, when we use Ampere's law, we have to define a loop around which to do the integral so that we ultimately can solve for the magnetic field on the perimeter of that loop. How do we use it? Well, let's pick a really high symmetry case. Like I said, we already know the answer to this from the Biot-Savart law, and that is a very long, essentially infinite straight wire carrying a steady current I. So we can use Ampere's law to find the magnetic field a perpendicular distance r away from the wire. And the habit that you want to always get into when using Ampere's law, just as we did with Gauss's law, is first sketch the current configuration and then sketch in the B field lines that you know about from symmetry. So here's a long straight wire. The side view looks like this, and we imagine that there's a loop that circulates around the wire, and we put the dotted lines here to remind ourselves that this is not something physical. There's not really a hoop out there physically, but we're just going to imagine a loop like that so that the end view looks like this. Why do we draw these lines? These represent the magnetic field, right? We know from the Biot-Savart law that the magnetic field of a long straight wire makes circular loops around the wire. And so the end view, which would be looking at this wire from the left-hand side, we would see the current in the middle going away from us, and the magnetic field lines would be these concentric circles centered on that wire. And that suggests that what we want to do in order to use Ampere's law is use a circular loop around the wire in order to evaluate the integral, the line integral that is in Ampere's law. So here's the sketch. The dotted line now represents the Amperian loop that we're going to use to evaluate Ampere's law. So on that loop, at that point everywhere, the magnetic field will be tangent to that circular dotted line, and the dl vector points along the direction that we're doing the integral. Here we've said we're going to do a circular loop, and so that writing down Ampere's law, we can see that the b vector and the dl vector will always be parallel, no matter where we are on that loop. And that makes the simplification of the line integral much faster. If b and dl are parallel, then the left-hand side becomes just the integral of b times dl, because remember the dot product involves the cosine of the angle. Cosine of 0 is 1. The right-hand side, now here's what the I enclosed means. We have defined a circular loop, and what is the current that passes through the inside of that loop, that passes through the surface that that loop defines? And that is simply the current I. So on the right-hand side we get mu naught times I. Now, by symmetry, we can also realize that since every point on that circular path is the same distance r away from the wire, by symmetry we expect b to have the same magnitude everywhere on the loop, so it can come outside the integral. b integral dl mu naught I. Remember now, this integral is a closed loop of this distance dl all the way around the loop, and so summing that up all the way around the loop just gives us the circumference of that path. So it's b times 2 pi r equals mu naught I, and then solving for b we get b equals mu naught I over 2 pi r. You'll remember, hopefully, that this was the result that we got when we used the Biot-Savart law to find the magnetic field produced by a straight current segment. Then when we took the limiting case as that segment became infinitely long. So that's the simple result, mu naught I over 2 pi r. This example doesn't prove Ampere's law, but it does illustrate how we use it starting from the top equation, which is the general statement of Ampere's law, to ultimately being able to solve for the magnetic field. And you'll notice that, again, even though this looks like a complicated integral to solve, when the symmetry of the magnetic field is large enough, it becomes a relatively easy matter to do. And just like with Gauss's law, there's lots of problems we can't use Gauss's law to solve for the electric field because the symmetry of the charge distribution isn't very high. And there's lots of crazy current configurations that you can imagine where Ampere's law, although being true, won't really help us solve for the magnetic field. But when we can use it, it makes the problem very easy and streamlines the solution of the magnetic field. So remember, Ampere's law is to the Biot-Savart law as Gauss's law is to Coulomb's law. We'll do some more examples in class.